Hi guys, welcome to my sixth episode of Love the Byte series. My name is Samuel Kamochu. I'm a telecoms and a software engineer. I'm also the co-founder and the lead presenter at Meliora Technologies. In this episode, my objective is to help you appreciate a byte, nibble, and hexadecimal and their relationship. But if this is the first time that you're watching my series, I would recommend that you go back to episode 1 because there are some concepts that are incremental and they are very critical for you to appreciate what is covered in this video. So allow me to move on to the subject of the day. A byte is a binary term. We just take the first two letters of each word. We replace the I with Y to avoid confusion with the bit, which we covered in a previous episode. So computers deal with groups of bits. A bit is too small to use within the computer. Now, in modern computers, a byte is acceptable, is an 8-bit number. And this is a worldwide concept that is acceptable in all parts of the world. But then you might be asking, why 8 bits? 8 bits were enough to hold any character. And this is something that the computer scientists and mathematicians debated and agreed that yes, 8 bits were enough to hold any character with the 256 possible values. Of course, this was before the computer had spread to all parts of the world. And mainly at that particular point, the computing was in Europe and America. So these 8 bits were sufficient to hold all the characters. So application of bytes. A computer stores data in memory, or what we call the random access memory. And each of the location in memory is a byte. So a byte is the smallest addressable unit of memory. So when you're reading data, the smallest group of bits that you can read is a byte. So programming also, a byte is the smallest addressable unit in memory. In a number of languages, you'll find that a byte is a data type. So when you are having data types, the smallest data type in programming is a byte. And this is not to be confused with Boolean, which has takes 2 values, true or false. A nibble is a 4-bit number. So if I take 168 as a decimal number and I convert it into binary, I get 1010, 1000. If I break this into 2 equal number of bits, so I have 1010 and 1000. Those are 2 nibbles. Why introduce a nibble? And the answer is it's because it's a 4-bit number. So we know that 4-bit number, the value range is from 0 to 15. This is from previous episode that I believe you've watched, 16 possible values. We also know something quite interesting, that a nibble taking 0 to 15 values can actually be represented as a hex symbol, because we also know that hex symbol, we have 16 symbols, 0 to F. So the human mind finds it very difficult to deal with a series of zeros and ones. So a byte, which is 8 bits, if it can be grouped into 2 nibbles and each of the nibbles represented as a hex symbol, it makes life much easier. And let me illustrate that. Let's take 168, 1010, 1000. If for those of you who might be knowledgeable of converting binary to decimal, so you can take 1010 is the same as 10, and 10 in hex is A, and then 100 is 0. And you can note the place value of the first 0 is 1s, 2s, 4s, and 8s. 8 and 2 are set, which gives us 10, and 10 we know that it is represented as A. You can do the same for 8. So basically, instead of writing the series of 1s and 0s, we end up writing A0. And this is definitely much better for human eye and the mind. So let me put all this together. So we know that all data in computer is represented as numbers. And this is what you say that it's in digital form. These numbers are represented in binary form, and this is because we learned that computers work very well with binary numbers. Binary data is grouped into bytes. Another thing that we've learned, that computers don't deal with bits individually. We deal with groups of bits, and essentially the smallest group is the byte. Each byte can be represented as 2 nibbles, and those 2 nibbles, each of them can be represented as a hex symbol. And this is one of the most important lessons as we move to the second and the third sections of this series. So allow me, before I tell you why we are covering all these things, allow me to help you differentiate hex and decimal number. So sometimes you'll find that 56 is a valid decimal number and 56 is a valid hexadecimal number. So how do you differentiate the two? So basically what we do is we assume that when you see a 56, it's a decimal number. If you want to differentiate a decimal number with a hexadecimal number, you add 0x and then you put your number. So anytime you see 0x56, it means it's a hexadecimal number. Anytime you see 56 without the 0x prefix, it's basically a decimal number. So why are we learning all these things, nibbles, hex, and bytes? I will demonstrate that with an illustration. I have a page that I've created which can be accessed using the above URL. And when you access the URL on your laptop, you'll get hello Natujenge as the content that is returned. Note that when I was doing these tests, I captured the network trace using Wireshark. Wireshark is a tool that you can download on your laptop that can be used to capture the network traffic or a trace on the network level, the bits, the ones and zeros that have been sent over the network against a certain network interface card. So in my case, I was able to capture traffic going out to the internet using Wireshark, and this is something that we're going to cover in a later episode, but you can feel free to download Wireshark. So in this case, this is a screenshot of I've captured a screenshot of Wireshark, and you can see at the top there I have filtered packets that are going to my IP, and the protocol is HTTP, and I have 4 frames. Essentially, the first frame is the GET request for the page, and the second frame is the response. Then I have another request for favicon or favicon, and the response for the favicon. So basically, I have 4 frames, but I'm interested in the second frame. So if you look at the second panel here, you can see that there are layers. We have the IP layer, we have the TCP layer, we have the application layer where we have HTTP protocol. And as part of the HTTP protocol, we have the data, which is just a line, which is hello Natujenge. But our focus today is the lower panel, which has a lot of zeros and E's and F's. By now, you should have recognized that these are hex symbols, or basically, these are nibbles, as we've learned. So let's focus on hello Natujenge. And when you look at the hello Natujenge, by now, if you remember the previous episode where we said hello is normally represented in as 48, 65, 6C, 6C, and 6R. You can see the same here. So we are using the same character encoding system, and you can see that we have 48, 65, 6C, 6C, and 6F as represented there. So you can assume that 20 represents a space, 61 represents capital N, A is 74. So we can basically see that each and every character is represented as a byte. So this is something very important, and I believe by now you should not fear these values that you have there. So the other thing that I want to look at, I expanded the IP layer and I was able to highlight the source address. Please note that Wireshark has already done the decoding for us, but you can see that 51, the IP address is represented as 330F D3, and A8. For those of you who can remember that the hexadecimal computation, the first three is the place value is ones, and the second three, the place value is 16s. So if you do the multiplication, 3 times 16 is 48, plus 3 times 1, which is 3. 48 plus 3 becomes 51. And you can do the same for the others. So you have 0f, f is 15, so you have 15. A3, we have A is 10, 10 times 16, that gives us 160, plus 8 gives us 168. So it's not difficult for you to actually tell or decode the IP address given the hexadecimal stream or the dump of the hexadecimal data that was transferred through the network. So you can see that all these data was actually transferred as I made the HTTP request. Each of the nibble represents something. So we just analyzed part of the IP header in binary format, and we also looked at the HTTP body. I believe you've seen that with the letters. And the HTTP header is wide. So we looked at the source address, but we have other things like the first nibble, 4 bits, represents the version. So one of the things that I want us to tackle in this slide is that sometimes we have parts that are less than 4 bits. They are not represented in either 4 bits or 8 bits or multiples of 8. So in this case, we have 3 bits, which is the flag, and the fragment offset, which is the 8-bit. Together, 16-bit in total. So basically, the 16 bits are 2 bytes, and you have to break it into bits. You have to represent it as bits for you to actually get the flags. So this is what you're going to do in this. We go back to Wireshark. If you look at this, you can see that the symbols that we have are 4000, representing both the flags and the fragment offset. So I will expand it for you. So you can see that the flags, if you convert this into binary, 40, we know that 1s, 2s, 4s, 8. So 0100 represents 4. And of course, quadruple 0 represents a 0. And the same case is repeated for the other 2 zeros. So if you are to look at the 3 bits, so we have to move 3 bits on this side and move the 1 bit on this side. So we basically have the first 3 bits are the flags and the others are the fragment offset. Now, these 3 bits, they have special meaning according to the specification document. So the first bit is reserved, which is 0. The second bit is 1, which is set, and it means don't fragment. And if you don't fragment, then the third bit says more fragments. Of course, it will be 0 if the second bit is set to 1, meaning that there are no more fragments because we are not supposed to fragment. Of course, the fragment offset will also be 0 because we are not meant to fragment. So basically, our message, hello Natujenge, is not being fragmented at the IP layer. So converting nibbles to binary is easy. This is an important skill that you need to have if you're to analyze binary protocols. So in binary protocols, you'll find some information is encoded in a bit. So you have to be able to know the bytes, the byte, the nibbles, convert them into ones and zeros, and map each of the bit to the value represented by the specification. And this brings me to the end of this episode. In case this content sounds interesting to you, or you believe it could be beneficial to someone else, please share with them. And also feel free to like, comment, and subscribe. Thank you very much, and see you again in the next episode.